The key focus of the efforts we're doing here are to better understand the role of sea ice in relation to the exchange of CO2 between ocean and atmosphere. The ocean is a tremendous buffer for the increase of CO2 in the atmosphere. It takes up most of the CO2. But we also believe that the cover of sea ice is a very important regulator in the ability of the ocean to take up CO2. So what we're investigating is a number of chemical, biological and physical processes related to sea ice and how that affects the CO2 exchange between the atmosphere and the ocean. When sea ice forms, it forms a very dense saline brine, which is heavy. That contains all the nutrients and the gases, including the CO2 and the inorganic carbon. And due to gravitation, this dense brine sinks out of the sea ice and it sinks deep. And along with it, it takes the CO2. That's sort of the principal process for how CO2 is transported from the sea ice into the ocean. In the spring, when the sea ice then melts, the meltwater is undersaturated with CO2 and that drives a huge uptake of CO2 from the atmosphere. Yes. There's a number of different processes that can regulate this. One is the inorganic carbon chemistry in the brine channels, which is also the thing we're looking at. And then there's the biology, algae and bacteria that either fixate or produce CO2 as a part of the metabolism. So all of this together makes a very entangled puzzle of how important the sea ice is for the CO2 exchange. The ultimate aim is that we will try to quantify how important this process is for the global CO2 findings. Our preliminary model calculation tells us that this process alone can account for the entire CO2 that we want to cut back by implementation of the Kyoto Protocol.